to perform a thermostructural analysis of a computer heatsink. This particular computer heatsink is made out of aluminum material, and these are the different boundary conditions that we need to apply on this particular heatsink, and then we need to find out the temperature distribution inside this heatsink. And once we find out the temperature distribution, then we need to find out the stresses that are going to arise due to the application of this thermal conditions on this particular heatsink using thermostructural analysis inside ANSYS Workbench. To perform thermostructural analysis on a heatsink, I have opened this ANSYS Workbench and I am going to drag and drop the steady state thermal analysis onto the project schematic. And I am going to open the engineering data, go to the engineering sources, and I go to this general materials library, and in the general materials library I am going to select the aluminum alloy. And once I select this material, I am going to close this particular engineering data. Right now what I am going to do is I am going to right click on the geometry, say import geometry, and I am going to select this particular heat sink. And once I select this particular heat sink, then I need to double click on the model cell in order to open mechanical. So once I open ANSYS mechanical, then we are going to do the further analysis. See, once the ANSYS mechanical has opened, now what I am going to do is I am going to go to the geometry branch and I am going to change this material from structural steel to aluminum alloy. And once I did this, I am going to right click, say generate mesh. Once I have measured the body, I am going to right click on the steady state thermal, going to insert, go to this heat flux option, and I am going to select this bottom face on which I am going to apply the heat flux. So the value of the heat flux that was given to us is 1000 watts per meter square. So what we need to do is we need to change the units from millimeter to meter, and then we need to enter 1000 watts per meter square. Then once I have applied the required heat flux condition, then I need to apply the convective boundary condition, for which I am going to right click, say insert, go to the convection, and I am going to select all these faces. So once I select all these faces, then I will be able to apply the convection condition. So I am going to select all these faces. So once I have selected all of these particular faces, I am going to press apply, and once I got to apply, I think I need more faces to select. We have got all the faces. Now the film coefficient that was given in the problem is 30 watts per meter square degrees centigrade. So I need to enter 30 here, and the ambient temperature is 28 degrees centigrade, and the ambient temperature is 28 degrees centigrade. And once I have given all these particular conditions, I am going to right click and say solve. Once solution is done, you can just right click on this particular solution branch, say insert, go to thermal, go to temperature, and you can just right click and say evaluate these temperatures, and this is the distribution of the temperature inside this particular heat sink. You can also see the animation of how the heat is being flowing into this particular object from the bottom side. Even you can also use the vector display if you are going to calculate the heat flux, because heat flux is a directional property. And once we have finished this thermal analysis, in the next lecture I am going to teach you how to add these results to your structural analysis and find out the thermal stresses inside this particular heat sink. With this thermal analysis, I am going to close this ANSYS mechanical. Now what I am going to do is I am going to take this static structural and just drag it and leave it in the solution cell of this steady state thermal analysis system. So what happens, this engineering data, geometry, mesh model, everything will be shared with this particular static structural, and in addition to all of these things, this particular temperatures that are present inside the body will be acting as an input for our structural analysis. And once I have selected that, I am going to double click on the setup of this static structural analysis system, and it is going to open ANSYS mechanical. So here if you can observe in the outline tree, we have two analysis systems instead of one analysis systems. As this is an coupled analysis, we are going to get access to these two systems. Then coming to the structural, I am going to right click, say insert, and I am going to take a fixed boundary condition, and I am going to fix this particular phase, and I am going to say apply. And once I have fixed this particular phase, if I have any additional structural loads, I can apply those structural loads, or otherwise if I want to find purely the stresses that are only formed due to the temperature variation, I can leave it like this, and I am going to right click, say solve. So now the solution is done. Then I can just right click on the solution branch, say insert, go to deformation, and I can find out the total deformation. And also I am going to right click on the solution branch, go to stresses, and I am going to find out the equivalent stresses. I am going to right click, say evaluate all results, and I can see the total deflection. This deflection is only due to the temperature that is present inside this particular body, and this is the stress which has been purely caused by the temperature that is present inside the body or on the body. See here, the stresses are somewhere around 8.9 E7 pascals. We can change the units from meters to millimeters, so that the units of stress will be in MPa, and the stresses are around 89 MPa. So this is how you can perform thermostructural analysis using ANSYS Workbench. In the next lecture, we are going to see how to perform a thermostructural analysis on a bimorph. Thank you. Problem, we are going to perform thermostructural analysis of a bimorph. So this particular bimorph structure is prepared out of silicon with these particular properties, and the thickness is 1 mm, and we have a fixed temperature at this both ends, and we are going to ignore the convective mode of heat transfer, and we are going to find out the temperature distribution inside this particular bimorph. And by performing structural analysis, we are going to find out the stresses and strains that have been induced due to the presence of this temperature conditions in this particular bimorph using ANSYS Workbench. Bimorph problem, I am going to take the steady state thermal and place it on the project schematic. And once I place it on the project schematic, I am going to double click on the engineering data. I am going to add the new material known as silicon. So once I add this particular material, see here, as I am right now in the thermal analysis system, I do have access only to these thermal properties. But here I want to perform both thermostructural analysis, for which I need to give the structural properties of the material also. For that purpose, what I am going to do is I am going to switch this particular option off, which is nothing but filter engineering data. So if I turn it off, so what happens, I will have access to all the options that are present inside this materials toolbox. And once I have turned it off, I am going to select this isotropic elasticity, drag and drop it on the silicon, and then I am going to select this secant coefficient of thermal expansion, and I am going to drag and drop onto this silicon material. Then I am going to go to the thermal, and I am going to select this isotropic thermal conductivity, and I am going to place it on the silicon material. And once I have placed everything, I need to give the values here as an input. So the coefficient of thermal expansion is 2.6 into 10 to the power of -6, which can be denoted as E minus 6 for silicon. And then the Young's modulus is 200 GPa, so I can give it as 200 E9 pascals. And then the Poisson's ratio is 0.27. Then the thermal conductivity in the units of watts per meter centigrade is 130, so I am going to enter the value 130. And once I have given the required properties, I am going to just close this engineering data. And right now I am going to right click on the geometry, go to import geometry, go to browse, and I am going to select this bimorph. And once I imported the data, I am going to double click on the model cell in order to open this ANSYS Mechanical. Once I have opened ANSYS Mechanical, I am going to go to the geometry, and I am going to change this material from silicon, say structural steel, to silicon, and I am going to right click and say generate a mesh. So once I generate a mesh, I am going to give the boundary conditions. Here I want to refine the mesh, so I am going to select the mesh, and I am going to give a relevance of 100. So once I give the relevance of 100, I am going to just right click and say generate mesh. And once I generate the mesh, I am going to right click, say insert, and I need to insert a temperature condition where at this particular phase, which is the hot side, I am going to have a temperature of 60 degrees centigrade. And at this particular cold side, I am going to have a temperature of 10 degrees. So I'm going to select this face and apply the 10 degrees. Then what happens, in addition to these two temperatures, we have an internal heat generation in this particular bimorph. I'm going to right click on steady state thermal and say insert, go to this internal heat generation, and I'm going to select the total body and apply. And my heat flux value is given in watts per meter cube. So what I am going to do is I am going to go to the units and change the units to meters once again, and I am going to enter 100 here. So once I enter 100, I have given all the required thermal boundary conditions. Now what I am going to do is I am going to right click, say solve. So once I solve this particular problem, I am going to right click and place the temperature in this particular solution branch. Right click, say insert, go to thermal and go to temperature, and I am going to just evaluate all results. So this is the distribution of the temperature in this particular bimorph. Now what I am going to do is I am going to just take this particular temperature values as input, and I am going to perform structural analysis in the next lecture. This ANSYS mechanical, and then I am going to drag and drop this static structural onto this solution cell of this steady state thermal analysis system, and I am going to double click on the setup, and I am going to apply these physical constraints which are going to be applied in structural analysis, and we are going to see what are the thermal stresses and thermal strains that occur inside this particular bimorph. Once the ANSYS has opened, I am going to right click, say insert, and I am going to go to fixed support, and I am going to select this face as well as this face, and I am going to apply the fixed boundary condition there. And see here, in this imported loads, you will be having the load that is imported from this steady state thermal. So what is happening, as you are doing a coupled analysis, the first system is going to send its output as an input value to this particular second system, and once you have done this, you need to right click, say solve, and once you right click and say solve, you can get the stresses as well as the strains that are present inside the bimorph due to this particular temperature loads. So once the solution is done, I am going to right click, say insert, go to this stresses, equivalent stresses. Also I am going to right click, say insert, go to strains and equivalent strains, and I am going to just right click, say evaluate all results. And if I click this equivalent elastic strains, these are the strains present inside this particular body due to the temperature or thermal loads, and these are the stresses that are present due to this temperatures present inside this particular body. If you have any additional loads inside the static structural, you can also apply to find out the effect of a combined loading on this particular objects. So this is how you can perform thermostructural analysis in a very easy manner using ANSYS Workbench. In the next section, we are going to see how to perform structural and thermal buckling analysis on different objects using ANSYS Workbench. Thank you.